In modern systems architecture, the concept of absolute security simply does not exist. It is a mathematical and practical impossibility. Instead of chasing an unbreakable fortress, modern cybersecurity engineering operates entirely on a risk reduction paradigm. The goal is to minimize the attack surface to a point where the cost of a breach exceeds the value of the data. According to ISO 27001 and NIST, the CIA triad is the bedrock of information security policy. Confidentiality restricts data access to authorized entities. Integrity prevents unauthorized modification of that data, and availability ensures those authorized users have continuous, uninterrupted access to the system. Every security protocol, encryption algorithm, and access control layer we build exists solely to defend these three specific nodes against a digital environment that is inherently hostile. Consider a theoretical baseline system, a standard client-server web application where a user logs in by transmitting a plain text username and password. Relying strictly on this kind of static logical access control is brittle. It predictably fails the confidentiality test. Because the credential never changes, it is highly susceptible to network wiretapping or packet sniffing while moving from the client to the server. To mitigate this specific vulnerability, which is both a transmission risk and a human risk, engineers apply the concept of defense in depth. A primary layer in this defense is multi-factor authentication, specifically the use of one-time passwords, or OTPs, a requirement outlined in ISO 27001 Annex A.8.5 for secure authentication. An OTP generates a dynamic, time-limited hash directly on the client device. If a bad actor executes a man-in-the-middle attack and intercepts that OTP packet, the countdown expires before they can reuse it, neutralizing the stolen credential. While the OTP effectively secures the endpoint identity against reuse, the transmission channel itself remains fully exposed to data extraction. To protect the payload in transit, the system requires a cryptographic layer. We have to protect that channel from interception by encoding the plaintext data into unreadable ciphertext. Systems engineers typically choose between two primary cryptographic tools for this: symmetric encryption, like Advanced Encryption Standard, or AES, and asymmetric encryption, like RSA. Choosing between AES and RSA is not a matter of security preference. It is a strict computational trade-off that dictates the speed and scalability of the entire system. This flowchart outlines a simulation methodology from a study published in the Jati Journal, designed to measure the exact execution times of these two algorithms under varying data loads. Looking at the results in this chart, we see something counterintuitive at the microscopic 1 kilobyte data scale. AES is actually slower than RSA here, taking 0.0046 seconds compared to RSA's 0.0018 seconds. This anomaly is caused by what engineers call initialization overhead. Before encrypting the first block of data, AES requires upfront computation to set up its state matrix and substitution box in the system memory. At 1 kilobyte, that setup time dominates the process. But as we increase the payload to 5 and 10 kilobytes, the AES initialization finishes. Its processing time drops drastically and stabilizes at roughly 0.0001 seconds, leaving RSA behind. By the time the payload hits 10 kilobytes, RSA is approximately 11 times slower than AES. Because of this compounding computational lag, RSA is unscalable and highly inefficient for encrypting bulk payload data across modern networks. So why does RSA place such a massive burden on the CPU the moment the payload increases? The answer lies in the mathematical architecture. RSA relies on an operation called modular exponentiation using massive prime numbers. Computing the mathematical powers of numbers that are thousands of bits long requires grueling, sustained CPU cycles. It is mathematically exhausting by design. AES uses a completely different structure known as a substitution permutation network. Instead of heavy prime factorization, AES processes blocks using highly efficient bitwise shifts and simple XOR logic operations. These are native and extremely light for modern processors. This presents a paradox. If AES is that much faster, why do engineers use RSA at all? AES is a symmetric algorithm, which means it suffers from the key distribution problem. For AES to work, both the sender and receiver need the exact same cryptographic key. But transmitting that single secret key securely over an open network is impossible without encrypting it first. Engineers are caught in a trap. They can choose AES for unmatched speed but broken key distribution, or RSA for secure key exchange but crippling computational lag. To resolve this cryptographic dilemma, systems architecture relies on the hybrid cryptosystem. The process begins with the first phase, initializing an asymmetric RSA connection strictly to handle the key exchange. The client and server use RSA's public and private key pairs to establish a temporary, highly secure mathematical tunnel. Through this secure tunnel, a single symmetric AES key is safely transmitted to the receiver. Now the second phase begins. With the AES key safely shared, the heavy, CPU-intensive RSA protocol is immediately discarded. The system switches entirely to AES, utilizing the shared key for high-speed, bulk payload encryption for the remainder of the session. We can now look back at that theoretical baseline system we started with, the vulnerable plaintext login. We layered strict logical access controls and dynamic one-time passwords to verify and secure the endpoint identity. Then we wrapped the transmission in a computationally optimized hybrid cryptographic channel. By mathematically balancing processor constraints with layered access controls, we achieve a resilient digital architecture, one that successfully upholds confidentiality, integrity, and availability.